All right, last example, number 5 in 10.3, and I think it gives us a really good real-world use for the composition of functions. So it's telling us that a spherical weather balloon is being inflated, and then the balloon's radius is changing based on a function related to time. And I want to rewrite that just a little bit, that really what that is the radius is a function of time, and that's equal to the square root of t. All right, now they want us to express the volume of the balloon as a function of time. And I really think it's important that don't worry if you don't know what that formula is, because there is no formula. It depends on how quickly you're filling the balloon, right? The formula that we have for the volume of a sphere, I'm going to write it here. The volume of a sphere is equal to 4/3 pi r cubed. And I'm going to write underneath it that really what that is the volume of the sphere as a function of the radius of that sphere. And again, I'll just write the 4/3 pi r cubed there. Now, neither of these give us the volume of the balloon as a function of time, but recognizing that the variable r is changing based on time means that if I want to know the volume of the balloon as a function of t, so if I want to know v of t, what I'm going to do is take function v and put that r of t function in. And that's why this is in 10.3, that v of r of t is a function composition question. And what that's going to look like, I'm going to write it as 4/3 times pi, but instead of r here, I'm going to put a big bracket just to make sure I have enough space, and I'm still going to cube it, because what that expression is, that's v of blank. I haven't put anything in there. So if I wanted v of r, I would just go one step up, and it's this guy, right? It's r cubed. But if I want v of r of t, I'm going to take the function r of t, which is the square root of time, and that's going to be what's cubed. So that right there is v of r of t, and that's perfect. That is a way of describing it, but it's also the volume of this balloon as a function of time. Now, I'm going to do one more thing to this. When I take the square root of time, that's effectively giving it the exponent of 1/2. So now I have a power on a power, and I'm going to write the volume of this balloon as a function of time is 4/3 pi times t to the power of 3/2. And that's just going to make it a little bit easier to do any algebra manipulation too, which is really how we finish the question off. Right now, I really want to push that this formula is not true for every spherical balloon out there. Right? If we could inflate the balloon faster or slower, our r of t function would change, and our v of t function would change as well. And that's a really important consideration. That, and I mean, this is a little bit far afield, but when you go to the gas station, you throw the pump in your vehicle, and it takes you 20 minutes to fill up. Right? So the volume of your tank as a function of time is pretty slow. But try to think about NASCAR. Right? They have those pit crews that are able to fill up those cars mostly because the fuel is literally pushed into the vehicle, but their volume as a function of time function is very, very different, because 5 seconds in a race can make or break you. But when I'm filling up my vehicle, I don't need that speed, so they use a different way of getting that gasoline into my vehicle. And I know that seems like it's not related, or who cares, Ms. Shimko, that doesn't matter to me, but it's so important that so many things in our world, our modern world, have been optimized to make them the fastest, the efficient, or the most profitable. And most of the time we do that via some kind of a mathematical process. All right, before I talk too much, that's not about this example, let's just scroll up. And for B, it says, after how many minutes will the volume be 4,000 cubic feet? So what B is essentially asking us, just kind of having trouble scrolling there, is it wants to know when V of t is equal to 4,000. Now, I always like, writing out what that's actually asking us. What we're going to do is we're going to combine these two concepts, and essentially we are trying to solve when 4,000 is equal to 4/3 times pi times t to the power of 3/2. Now, there's a lot of different ways of doing this, but my preferred technique is to isolate the variable first and then deal with the exponent after. So what I'm going to do here is I am going to do this maybe a little bit differently than you might like. I'm going to multiply both sides by the reciprocal of the fraction, which is 3/4. Now, when I do that, 4/3 times 3/4 is 1, so it's gone. 3 times 4,000 is 12,000. 12,000 divided by 4 is 3,000. So I get that 3,000 is equal to pi times t to the power of 3/2. I'm now going to divide both sides by pi. I will not be doing 3,000 by pi, or 3,000 divided by pi in my head. So I'm going to leave this as 3,000 divided by pi is equal to t to the power of 3/2. Now, the big push, I think, in chapter 7 and chapter 8 is to really get you comfortable with the idea of exponential manipulation. And to solve for a variable, I want to have that variable to the power of 1. So if I tell you x is equal to 4, I'm really saying x to the power of 1 is equal to 4. The way that I'm going to do that in this question is I'm going to take both sides and I'm going to put them to the power of the reciprocal of whatever's already existing on my variable. And the reason why this works is that a fraction times its reciprocal, which is a power to a power, is going to make the right-hand side of this t to the power of, and I'll write it as 6 over 6, because really what I'm doing there is 3 over 2 times 2 over 3, which is, 6 over 6. But that's not the best way to leave it. I would leave it as t to the power of 1. And that's solved now, right? T to the power of 1 is going to give us our solution. Now, the left-hand side, 3,000 divided by pi to the power of 2/3, is pretty ugly, and I would recommend using your calculator. The one thing I do want to write, I'm going to grab my calculator in a second here, but you could write that 3,000 pi to the power of 2/3 as the cube root of 3,000 divided by pi squared. Those are equivalent to each other. I'll just quickly write the exponent rule, which is x to the power of n over m is the mth root of x to the power of n. I know that we're doing digital learning this year and it's tricky, and I fully appreciate how tricky it is. These are the things that you need to come out of this with. Remembering how to manipulate exponents, the exponential, the power rules, the laws of logarithms, that's the stuff that matters, because that's the foundation for math courses beyond high school. All right, I'm going to plug that into my calculator. So 3,000 divided by pi, I'm going to square that. I'm going to take the cube root of that. And what I get is that it is going to take us 96.9722 or 97 minutes to fill that balloon up. Now, maybe you have to, get to the hot air balloon convention in 30 minutes. So you have to figure out a way to inflate the balloon faster. Maybe that's too fast and you have to do it slower. I don't know. But that is how long it's going to take us based on the information given to us in the question. All right, the assignment I'm going to leave up here for a second. I know it's got the review. I'm not overly worried about that. That's in your assignment sheet. Please do be checking Google Classroom, because we are modifying these assignments as we go.